Hello everyone, I'm Maximistas and I will present you our work on modular output mathematics and how they can lead to more incremental research over deep learning code bases. The problem is that it is often hard to build new experiments on existing deep learning code. Methods that are conceptually similar to one implemented in a code base can require big modifications of that code. Although library partially solved this problem by proposing many components for creating neural networks, optimizing their parameters, etc., difficulties remain when modifying code related to the way the network outputs are interpreted. Indeed, the loss, the creation of the target maps, and the decoding are interdependent functions. So changing one may quickly require to change the other. Yet, no software construct usually helps this modification. In this work, we regroup those functions under the concept of output mathematics and propose a modular organization to address this problem. To make sure you see what we are talking about, let us have a look at an example semantic segmentation code base. Let me highlight the instructions related to the output mathematics and explain you the problem. As you may know, depending on the loss, a particular format of the target and of the activations have to be provided. Furthermore, network activations are usually processed at very different places, and mathematical consistency must hold across those operations. So change is not easy. This is not an isolated case. The output mathematics often consists in such a set of functions that have to be carefully orchestrated, and between which the flow of data is then very constrained. Because of this, the overall codebase becomes difficult to repurpose for new research. We propose to resolve this problem by reorganizing the code behind output mathematics so that they don't require this careful routing anymore, hence eliminating the constraints on the flow of data. The output mathematics can therefore form a system from which mathematical variables like the loss here can be retrieved transparently. In order to achieve such convenience, we propose to organize the output mathematics in classes and to map mathematical variables to methods. This way, any variable can be accessed from anywhere, and any variable can be refined through the creation of a class modifying its behavior, like this no-relu variant. We call mixins such classes made to redefine variables of others. Mixins can do very different things. For instance, they can help to replace some predictions by Oracle, or they can help reworking the dynamics of some subtasks, or even introducing new tasks. Mixins can be reused and composed through experiments to answer the many questions you have. Of course, all of this may come at some cost. To assess that our proposal is viable and useful, we gave it a try on the Panoptic-Deeplab code repository. Panoptic-Deeplab is an efficient and conceptually simple baseline for panoptic segmentation. Sadly, its code is intricate and constrained, just as we described. So we first made the output mathematics modular, and we then took advantage of the added modularity of the code to move the computations of the ground truth maps to the GPU and to implement learnable centers that require a significantly different data flow than the original code. Indeed, the ground truth centers now depend on predicted offsets, and this change must also impact the ground truth offsets. Regarding performance, we measure timings and memory consumption across those different versions. As you can see between the two first rows of the table, there only seems to be a negligible overhead to organize the code in such a fashion. Furthermore, being able to move the computations helped us to make the training 3 to 5 times faster and to broaden the space of explorable output mathematics. All of this while only incurring a relatively small memory overhead on the GPU side, which often constitutes a bottleneck. As a final note, we would like to add that when working with such complex output mathematics, it can be tedious to keep track of where and how each variable is computed. To document them, we propose to provide a visual representation of the variable definitions and the associated method names that each class provides. With all of this, anyone can quickly identify the terms he needs to modify and quickly test an idea on someone else's code, with basically the same convenience as one can switch optimizers or neural architectures. Thank you for your attention. If this sounds interesting to you, please don't hesitate to come at the poster session.